we are discussing the Ginzburg-Landau theory of superconductors. Particularly, we are interested in the electrodynamics of superconductor, and what I will show is finally show you is that there is a state in which the magnetic field does penetrate superconductors, and we will find out when and how does it happen. So, in that context, we have written down the Ginzburg-Landau free energies, wrote down the equations of motion. These equations, one gives me the equation for psi, another gives me the equation for the current. Okay. So, then we have taken the equation for psi and for situation where there is no field, and solved it, not yet solved, but wrote it down and immediately found out there is a length scale that appears in the problem, and that length scale is this C. It is called Ginzburg-Landau coherence length, and that varies with temperature as T minus T c to the power minus half. Okay. So, let us go ahead and find out how psi behaves inside a superconductor. So, f function as you can see is a ratio of two quantities, one is psi, another is the bulk value of psi deep inside the superconductor, which is psi infinity. So, that means it is I can write it as f x equal to 1 plus some g of x, where g of x is much less than 1, because f x equal to 1 is the value deep inside the superconductor, and we assume that the inhomogeneity is not so strong that it destroys superconductivity completely somewhere inside. So, in that case g x will smoothly vary and vary in within a small range, and so therefore, g of x is much less than 1. Okay. They are both dimensionless quantities, f x and g x are dimensionless. Then we can rewrite this equation by expanding this cubic term 1 plus g cube, and this is what has been done, c square g d2 g dx2, this plus 1 plus g minus 1 plus 3 g equal to 0. And you can solve this equation straightforwardly. This is now a linear equation, and you can solve it giving g of x going as g of x going as e to the power plus minus root 2 x by c of t. Okay. So, that is the solution that is for g. As I said, the g is the deviation from the infinite values. So, that means the over a length scale of c, the function f basically restores its value of the psi infinity. So, if you are coming from deep inside the superconductor, the g x see if it is you are going inside the superconductor, g this minus sign is to be taken, and then it decays within a g decays within a distance of c. Typical decay, I mean it is exponential decay. So, nearly 1/3 is gone by the time you reach x equal to c, and that is that means that it attains its full value psi infinity within a distance somewhat beyond c of t. So, that is c of t is a measure of the distance by which the superconducting wave function attains its full bulk value. Okay, one can define these parameters in terms of other quantities, and those I am not getting into. These are for experiments, these are extremely important, because there are measurable quantities like h c and lambda effective in terms of which c of t can be defined, and so these definitions are given in books. So, it is not important to realize to go through this algebra in the sense that this is you have to know what lambda effective is and so on. This is a London penetration depth in a superconductor where there are disorders, and so these are somewhat more phenomenological parameters, but these are things that experimentalists actually need and they can find out. So defining C of t in terms of those quantities. The interesting thing is that there is a phi naught. Phi naught is a universal quantity. It is an universal quantity in the sense that C it is H C by E star. If E star was just E, this would be the Dirac quantum, flux quantum, whereas here of course each star is H C by 2 E, but it is still a fundamental quantity. It is just the half of Dirac flux. Okay. So there is a fundamental physical quantity that is now appearing here. And there is another quantity that is extremely important, and that is why one puts in this C of t here. One defines a kappa which is the ratio between these two and the lambda effective and C of t, and this actually defines the border between its value defines the border between a type 1 and a type 2 superconductor. So, for a type 1 superconductor, kappa is much less than 1 and then lambda much less than C, whereas in a dirty superconductor lambda can be greater than and actually much greater than C, and in type 2 also that is what happens, and kappa equal to 1 actually in actual practice kappa equal to 1 by root 2 separates these type 1 from type 2. So, type 1 and type 2 are basically determined by the value of kappa, and if kappa is much less than 1 you have surely type 1, kappa much greater than 1 you have type 2. The border is at the separation happens at 1 by root 2. So, this is a picture of how lambda and C behave in a type 1 superconductor and in a type 2 superconductor. As you can see, the C is large in a type 1 superconductor and lambda is small. It is somewhat reversed in type 2 superconductor, where the full value is attained quite quickly for the wave function and H decays in a over a long distance. Here it is just the opposite. It takes some distance C which is large for psi to attend its value at infinity. Now, value deep inside the bulk. So, this is how it is typical values in a normal superconductor which is not very dirty are like few hundred for lambda, few hundred angstroms for lambda and few thousand angstroms for C in a type 2 superconductor. Of course, in the high TC superconductors C is very small. So, they are inherently mostly type 2 superconductors. Okay. The other interesting thing is we can discuss type 2 superconductivity, and there is some quantity called Hc2 appears, which I will discuss briefly quickly. And so, this is how it behaves between Hc1 and Hc2. The flux there is a field called Hc1, there is a field which is Hc2. Between these the flux penetrates. So, if you are coming from large fields, you are reducing fields. So, at Hc2 you will first penetrate the field and then it will carry on till Hc1. So, let me just show you the other picture which is much more much easier to comprehend, and this is how a type 1 superconductor wave M versus H curve. It goes up to minus 4 pi m, and then that is minus 4 pi m is the value of magnetization. As you increase H, there is an Hc at which the magnetization drops to 0. Okay. So, this is negative because in a superconductor it is diamagnetic, and so it rises with the magnetic field, and then it rises means it goes negative, and then at Hc2 it is just drops to vertically drops to 0, whereas in a type 2 superconductor M versus H curve is like this. It goes up, then it starts dropping from Hc1, and it takes all the way up to Hc2, where Hc is between Hc1 and Hc2, and it goes to 0 in a type 2 superconductor at Hc2. So, there is a large region between Hc1 and Hc2 where flux has the field has penetrated the system. Okay. Okay. So, let us just look at that. As I mentioned that Abrikosov was the first in a remarkable theoretical paper who predicted that the magnetic fields can enter a superconductor, particularly in an inhomogeneous superconductor, and in a type 2 which is now called type 2 superconductor, and as we just discussed, these are like tubes that penetrate the superconductor, and therefore, there is a screening current around this tube, and typical distances between these tubes is twice the Ginzburg-Landau coherence length, and the tube's size is typically lambda, the London penetration depth, lambda effective actually twice of that. Okay. So, let us just do the calculation very quickly, because this is in presence of a Landau gauge, and remember A y equal to H x. So, you now have a magnetic field, and you are trying to solve that equation of motion again, and the equation is very similar to what we did for quantum Hall integer quantum Hall effect, and that is exactly what it is, except that this side has this 1 by c square. This equation had this 1 by c square into on this side, and so c square delta square was there. So, then c square has been taken to the right hand side, and this equation then is exactly what you get in integer quantum Hall effect case also. A y is chosen as H x, this is the gauge that is taken. So, then you can write down the same solution again, then y and z directions are plane waves, whereas x direction will turn out to be a displaced harmonic oscillator whose center is at x naught, where x naught is this k y phi 0 by 2 pi h. These are very similar to that calculation. So, I am not repeating it, you can look up. What is interesting is that you do not have to solve this, you know the solution. So, you do not have to do anything more. What is interesting is this right hand side. This is 1 by c square minus k z square into f, and this is the eigenvalue, and we know what the eigenvalue is. Eigenvalue is n plus half h cross omega c. So, you just equate this n plus half h cross omega c to that 1 by c square minus k z square that was there. Therefore, you can immediately pull out an h, because h cross omega c contained that h. So, you equated this quantity with n plus half h with 1 by c square minus k z square, and you will end up from this equation. So, these two equations you are using n E n equal to n plus half h cross omega c, and E n is also 1 by c square minus k z square from the previous page, this one. So, these you equate, you will get the equation that is written down here. So, this gives a value of the magnetic field, so H. So, now what we try to find out is whether magnetic field and the superconductivity coexist or not. So, let us see. The highest value H can have is when k z equal to 0 obviously, and when n is also 0, right. So, these are the possible, these are of course n is 0 is the lowest Landau level, and we can also set k z equal to 0 is a very large wavelength, for example, along the, that is the maximum that you can have in the z direction. It is like a free particle with a very large wavelength. So, the corresponding H value is called Hc2, and what does it mean? It means that at this value both F, which is the F is the solution, remember F is the F is what you are looking for. I mean the solution for F is already written down, psi is something is this. So, as long as F is non-zero, psi is also non-zero. Okay. So, that means in this, when this happens, this is the largest magnetic field for which F is non-zero actually. That means psi is non-zero. That means at this magnetic field, the beyond this magnetic field your F will become 0. That will be means that the superconducting wave function will vanish after this Hc2. Below this Hc2, the equations admit of both H and F, that means psi non-zero, and that is what means that this is called the nucleation of superconductivity. So, as if you have a very large magnetic field, you are so you are now reducing the magnetic field, and you are looking at what magnetic field suddenly the superconducting wave function becomes non-zero, and this is the way one you can think of it. Or the other way is you are increasing H and then so you have a superconductor, you are you have a very large H, and then you are bringing the H down at one particular point. Suddenly there is a superconductivity appears, and at that value is Hc2. So, this is this below this value superconductivity and magnetic field coincide. They coexist inside the system. How do they coincide? That we will see. So, this one can actually calculate the relation of Hc2 with the thermodynamic critical field Hc, and that relation gives you this 2 kappa into root over 2 kappa into H, and that is why the kappa equal to 1 by root 2 separates the two types of superconductors, type 1 and type 2, because when Hc2 becomes, when kappa is 1 by 2, Hc2 will be when kappa equal to 1 by root 2, then Hc2 will become Hc. So, it will then move here and you will get a type 1 superconductor. So, that is at 1 by root 2 Hc2 becomes Hc, and at for Hc2 less than that you are in a type 1 superconductor, and this is how the psi behaves with respect to H. As you bring it down in a type 1, at Hc it starts moving up, becomes infinite value of superconductor, and then so actually at Hc2 you go up, and then if you are decreasing, if you are increasing the field at Hc2 you will so since Hc2 is less than Hc, this is how it will behave. So, you are coming from high magnetic field decreasing, and only at Hc2 you can nucleate superconductivity, and the moment you do that it will immediately go to psi infinity value, is bulk value. That is because you are already way below Hc, and then of course, if you are increasing the field, then you have to go up to Hc to destroy it. So, that is how the Hc is defined, the field at which superconductivity is destroyed. So, there is a hysteretic region, whereas in type 2 the Hc2 is greater than Hc. So, if you are reducing H, you will start having superconductivity here, psi will become finite at Hc2 and go up and till Hc2 it will keep going up, till Hc it will keep going up, but till Hc1 it will start go up. But the interesting thing is that it retraces the path, there is no hysteresis, because Hc2 is much larger than Hc. So, so that is the distinction between. So, that is what that picture showed us. Okay. So, that picture is recovered from this calculation. Now, Ablyazov went even further. He tried to figure out how these fluxes penetrate the superconductor, how the magnetic field penetrates the superconductor, and he actually worked it out. I am not going to give to work it out in detail, that is a separate calculation, and that is something that is a knowledge that you should keep. The calculation is somewhat complicated and very very intuitive. So, just that he found out that there is a in the oscillators, the fact that you can put the oscillators center, the simple harmonic motion center of the simple harmonic oscillator solution that you get within a range. I mean, that range he found out, and that range gave him delta x into delta y equal to phi 0 by b. So, this is inverse of the flux, I mean the number of flux quantum basically. See, A into area into B is equal is the flux, total flux, and phi 0 by B. So, inverse of that is the number of flux quantum, okay. And each of these fluxes carry a flux quantum which is h c by 2 e here. And from there he did a beautiful analysis. It's just a remarkable calculation, and he found out that these flux tubes don't go uniformly inside. They don't form a liquid like structure, they can or a random structure. They go in regular arrangements, and these regular arrays they form a lattice, and that lattice is called the Abrikosov flux lattice. The turns out that for this kind of superconductors, the structure that is most stable is a triangular lattice structure, and that is slightly lower energy than the square lattice structure, and so he predicted that there will be a lattice structure, and now we know that this triangular lattice structure is available. This is experimentally measured, and the measurement is very simple actually. What you do is that you just put some iron files on the superconductor. So, take a superconductor, put some iron files randomly all over, small iron particles, and then take it to a type, suppose it is a type 2 superconductor, then thread the magnetic field. So, put a magnetic field below Hc2, and then the magnetic fluxes penetrate, and they penetrate in a lattice which is triangular, and then you just shake the superconductor, and the iron files will basically go towards the magnetic fields where the magnetic field has penetrated, and then you will see a pattern of these iron powders exactly as the pattern of the magnetic fluxes below, the arrangement of the flux tubes below, and that is how it is figured out easily. You can actually do it in your MSc lab or BSc lab, and if you have a low temperature phase, liquid nitrogen for example, and you can find this lattice structure. So, that is all we wanted to discuss about type 1, type 2 superconductivity and Abrikosov vortex lattice. This is again a remarkable piece of intuition and to confidence in your theoretical calculations, that you predicted it way ahead of the experimental. Even people did not even think about that kind of a situation. So, Abrikosov later got Nobel Prize, and this is really a remarkable piece of intuitive calculation. So, I stop my discussion of this Ginzburg-Landau theory here, and let us just go over to another very important applications of superconductor that I alluded to when I discussed this delta and delta phi uncertainty. So, let me just go through quickly what it is. It is called the flux quantization. So, let me just do the one that is important, which is what I was alluded to, which is Josephson effect. So, in Josephson effect, what one does is you just, as I said, you put two superconductors separated by a very thin insulating region, and then you basically it is so small that it is less than the length is less than the coherence length. So, that this superconductor and this superconductor can talk to each other, and then you can simply write a Schrodinger equation for the superconducting wave functions, and it is like a two state model again. and this is the actual geometry. Physically this is how it is done. There is a small insulating layer. You can basically etch out the superconducting regions, and that gives you a insulating region. Okay. So, let us just quickly go through the calculation. If you connect a battery, then the two potentials U1 and U2 that are arbitrary here, that their difference is at least QV, and one can just then set U1 and U2 at midpoint. I mean, the one is at minus QV by 2, another is at plus QV by 2. Q is the charge, charge corresponding to these wave functions. Okay. So, we have been discussing this for long. Okay. So, then the calculation is it goes as follows. You can write this psi 1 as root over ns e to the power I theta 1. Remember that mod psi that we were using, mod psi square was ns. So, mod psi square we wrote down as ns. So, psi can be then written as rho 1 and rho 2 are the two densities on the two sides, which are this ns 1 and ns 2. Okay. So, once we do that, these phases are all that we are interested in now. Okay. So, then write down the equations and define theta 2 minus theta 1 equal to delta. Go ahead and you can equate the imaginary and real parts to get these two equations. Real part is this and imaginary part will give you this. So, these equations are absolutely simple algebra, you can work it out. Now, the first two equations, as you can see, say basically rho 1 dot equal to minus rho 2 dot, but the current is rho 1 dot that flows across the barrier. That means, the reverse current you can think of is rho 2 dot flowing in the other direction. So, J of the current is then 2 k by h cross root over rho 1 rho 2 into sin delta, because that is what you will get from these equations, right. Rho 1 dot is this and that is the current. And the delta dot is theta 2 dot minus theta 1 dot, and that turns out to be q v by h cross, again from the second set of equations. Okay. And then you can integrate and get some delta naught constant of integration plus integral of v t. Now, if v equal to v 0, then delta is basically this quantity. Okay. It is a constant potential. So, this is a DC, basically DC voltage, and you get this, and you can write your J therefore as, you can put that delta in here, and J is J sin delta naught plus q 0. Now, the thing is that V 0 by h cross is very large. Of course, h cross is an extremely small quantity. So, this part oscillates extremely fast, and therefore, you cannot see this. Okay. Whereas, if V 0 equal to 0, see, this will average out to 0 if V 0 is finite. Whereas, if V 0 is 0, then you can have a current which is just J 0 sin delta naught, and delta naught is basically is this quantity. It is the difference between the two theta 1 and theta 2 at V is 0 now. So, it is just the difference between these two at t equal to 0. So, if initially there is a difference between the two phases, that will give you a current which can be between. So, the current can now be plus and minus, it oscillates between plus 0 and minus 0 depending on delta naught. So, it is a very contrary situation. If you have no voltage, you have a current. If you have a voltage, you have no current. So, this is what happens in the DC Josephson junction. This is really strange, but this is true. In AC field, you can just go ahead and do this calculation. It is again a simple calculation, another term will appear, and then you just for delta x small you expand, and what you get is finally this quantity. Now, again in this quantity, this will be oscillating very fast, this will also oscillate very fast, the last q v 0 t by h cross, q v 0 t by h cross, they will oscillate very fast and they will wash out. But if if somehow the what happens is that you can choose your delta 0 in such a way, then you can actually. So, this is on an average this is 0, because of this q v 0 t by h cross being very large. Rapid sign change will make it 0, but you can choose your omega to be this q by h cross into v naught, because the omega is the frequency you are applying from outside, the AC field, AC voltage, and then of course you can get these quantities where, for example, look at it, where if delta 0 is pi by 2, this is sine square. So, this will then show up in a oscillatory, but it is always positive. So, this will give you a current, there will be no cancellation due to change of signs, and you can have an AC Josephson effect with suitable periodicity coming from here. Okay. So, this is a remarkable situation again, because this, as I said, the DC one is really amazing, that if you have no voltage you have a current, you have a voltage you do not have a current, and of course, there is also an AC Josephson effect. And Josephson junctions are extremely important, because these are the ones that are used to measure the magnetic field, because if you have a magnetic field, then there will be an additional phase coming from, say, so suppose you have a ring, a Josephson ring, which is insulated. So, this is a Josephson ring, and you are threading a magnetic field through it. That means there will be a dot dl due to the magnetic field, and that phase changes the overall phase of this the theta 1 and theta 2 that we started with, and that therefore, you can measure this flux that flows through this ring, and it is extremely sensitive, that one can measure very small fields due to this. So, theta 1, theta 2 minus theta 1 minus or plus this additional field. So, your delta will change to delta minus a dot dl, and so make it plus. So, delta plus a dot dl, and that a dot dl can be picked up, because that is in the phase, and the current, the phase shifts means current, the profile of the current, where it goes to the oscillation points where it becomes minimum and maximum, those shift, and from that shift you can immediately find out what this a dot dl is, and therefore, what the flux is. That means so, this is curl a dot ds, right, and therefore, it is the flux, and then this is measurable. You beautifully one can measure the flux, and you can actually measure even extremely tiny fields by this kind of measurement. So, the application of Josephson junction is tremendous, Josephson rings, junctions, and so on, and that actually led to the person Josephson getting a Nobel Prize along with Esaki and Giever for this very simple, but extremely interesting and important calculation and suggestion, which was borne out by experiment.